Welcome to all the audience on YouTube. It's my great pleasure to welcome Tobias Kussel as today's presenter. He is a research scientist at the German Cancer Research Center in Heidelberg and is a physicist and computer scientist by background. His main research areas are genomic privacy, secure multi-party computation, and the dynamics of complex systems. His talk today is called Samply.Beam Communication Middleware for Complex Clinical Networks. So secure communication across different locations and network boundaries with regard to sensitive data is an important topic in NFDI, especially with regard to data security and integrity. I am very glad that today we will learn more about Samply.Beam as a communication layer in this area. So, and with these words, I'm very much looking forward to your talk, and now gladly hand over to you, Tobias. The floor is yours.
Yeah, thank you very much. Thank you very much for the kind introduction, and thank you very much for the opportunity to present this part of our work in NFDI. And as you said, I'm talking about Samply.Beam, our communication middleware we develop for various research networks, and it's designed mainly for medical networks, or that was the intent when we started designing Samply.Beam. But I think it can be applied to a lot of different federated research environments, and nearly every research group works partly with sensitive data. So because of that, Samply.Beam might be interested for all of your own research endeavors. So let's get started. Who are we, the developers of Samply.Beam? We are the Department of Federated Information Systems from the German Cancer Research Center in Heidelberg. It's headed by Professor Martin Lablans. And our basic mission of the whole department is to build bridges among DKFZ and other partners for data networks in research and care. And as you can see on the map on the right-hand side, we are involved in quite a lot of different research networks, most of them in a medical context. But for NFDI, we're in GHGA, the German Human Genome Phenome Archive, so a genomic and phenomic database and connection of that. And there we mainly provide pseudonymization and record linkage services, but also enable federated research networks with our experience in those areas. And as you can see, all those little dots are different sites we connect in those networks, and we have nearly a decade of experience connecting different university clinics and other research institutions in federated networks. And when we write some grant proposals or architectural schemes, we always see graphics like that, where we have some central components and some local components and different sites, and we draw a lot of different arrows and different systems, and all those graphics look really great, and jobs go in and results come out. But in reality, this communication is not as easy as it is displayed on those charts. Here, this is one of those classical architectural overviews. We have different components and connect them via arrows. But in reality, it quickly becomes really tedious and difficult to ensure reliant, robust communication between those sites. For example, site IA might introduce the need for a central proxy system, an HTTPS proxy, like I think most clinics and I think a lot of other research institutes have. So every other protocol other than HTTP and HTTPS gets blocked or needs special consideration to work with this environment. And every site has a proxy like that, all in those in their own different flavor. For example, site C wants to terminate the encryption of the HTTPS traffic and wants to look into it. So the mechanisms doesn't work end-to-end anymore, and site B introduced another different server for authenticating allowed traffic. So every component, every application that we have displayed by those site PCs needs to deal with those network requirements and those proxies, and need to implement the ways to deal with that. And the hassle doesn't stop there. In medical research, we often have very restrictive firewall rules because we deal with very, very sensitive data. So one of the usual requirements is that it's not allowed to have inbound communication at all. Only outbound communication is allowed for security reasons, and we have other firewall restrictions. So we always need to design our communication around those restrictions. So fulfilling those requirements in regard of security, but allowing the communication we need to have federated research, actually. And usually the task to implement all those measures lies at the application developers, developing the application and developing the communication services in that. So we did this quite a lot. And as you said, for each of these research networks, we have solutions in place. And for the last 10 years, we had solutions in place to deal with all those different systems we encountered. And finally, for the last 2 years, we thought about how to bring it all together and produce one software package dealing with all those issues and pulling out the complexity out of the applications into a different system, allowing the application developers to focus really on their core task of developing in our case, medical expert systems, in other research environments, other expert systems, just focusing on their actual work and not dealing with all those, as I call it later, plumbing. And so we developed Samply.Beam, and the graphics looks quite the same as before. So let's draw some markers of what are the Samply.Beam systems. We have 2 systems deployed centrally in each Samply.Beam network, a broker and a certificate authority. And each site just needs to operate at least one Beam proxy. And we had quite a lot of different requirements when we designed this Beam service. The one requirement was it should be really performant. It should give fast replies. One of our first use cases was a dashboard and a search environment for end users, and they don't want to wait for 15 seconds when they click the button. They want to see results immediately. So we need fast and reliable connections to give the results quickly. The second thing we really focused on was to develop a really lightweight solution. Most sites are really restricted when it comes to hardware and maintenance capacities. So we designed a really small application, both in size and in memory consumption. So I drew one Beam proxy for each site, but if it suits the site, they could spin up like hundreds of Beam proxies for each application one. If it suits their environment, it's a 10 megabytes binary with like 30 megabytes of memory consumption. So it's really, really lightweight and fast. And as I said, it was really designed for networks with strict firewall rules and exotic proxies and restricted data protection regulation. It's not an afterthought. It's not a off-the-mill product or that we banded to fit into those environments, but all those configuration efforts we needed with stock applications, we spent into developing a really good fit for those network environments. So we deal with sensitive data, really sensitive data. So the security of the data and the communication is paramount. And we ensured this by developing from the start an end-to-end signature and encryption scheme. So the confidentiality of the data is ensured and the authenticity and the integrity of the data is ensured. At every part of the chain, we can verify that a message has not been tampered with. So I think these security guarantees are really, really important for a lot of research networks. And as I said, our main gripe was that we had to implement all those measures for every application, and we wanted to pull that complexity out. So we built Samply.Beam to be completely content agnostic, meaning we don't require the messages we transport in a specific format or in a specific way or structure, but Samply.Beam doesn't interpret or use the payload, the actual transported data at all, and every kind of data that can be packed into a message can be transported. So we have one solution with at least one component at the side, mostly one component at the side, that deals with all the complexities of a federated network communication. We, based on our use case, we use a certain terminology when we deal with the messages we transport. We call them tasks that are created and results. This is a bit more specific than we actually do. It's just messages and everything can be transported, but so you're not surprised when in later in the presentation I talk of tasks and results. This all looks complicated. Certificate authority looks complicated, but the good news is for a user, that means for an application using Samply.Beam, this is all a black box. It's just a big black box between different sites, and the application just has to know its corresponding local Beam proxy. This is all. This is the gateway to the Beam network, and we can just transport messages across. So the laptop can create a task, send it to the Beam proxy, the local Beam proxy. There it gets encrypted and signed, and then it gets sent over the Beam network. Well, a black box is not really helpful to think about what is happening. It's not a good mental model to just have a black box. So let's give you a little bit of visualization of how you could think about these Beam broker system. It's like a shared email inbox. I think I really like this image, because you send a task, you send a message, it has senders, it has recipients, and those recipients can answer, and it's just like everyone in the Beam network is working in a shared inbox and can get the messages that are important to them and can answer them based on a authentication scheme. So, for example, here we have 3 tasks with certain metadata attached, and we can see the status of the work on these tasks, like here node A has returned a result, or here node B claimed the task, meaning I received it and I'm working on it, or here node C says, oh, I encountered an either temporary or permanent failure. So I think this is a good mental model going forward for what the Beam network actually provides. Now, the recipient Beam proxy received the message, and we can cryptographically ensure that the message has not been tampered with, that it has not been opened, that everything is still confidential, and the integrity is preserved. So at the end of this chain, we can decrypt the message and strip the signature and forward the message to the application dealing with this task or this result. So this is basically the usage of Samply.Beam in a nutshell. It's just a big black box and just works. That's a nice thing. And when we put it in production, we were quite surprised, and it was a very nice surprise that we found out that Samply.Beam is actually compliant with all those network and data protection concepts we already established. So we didn't have to jump through the regulatory hoops. It just worked out of the box and got approval for all those communication networks and research networks. And it was really, really easy to bring it into production. So, okay, it's difficult to talk about network communication in not that deep technical level. So let's show you just a little bit of application, why we actually developed Samply.Beam, one of those applications where ordinarily the communication is quite tricky and difficult. And this is the search interface we developed for DKTK, where we allow federated queries and data exploration. So, for example, here we can type in prostate cancer, get the diagnosis, and click on search. And we are not querying a central data repository, but Samply.Beam in the background sends this query to all the connected sites and runs the query locally and aggregates the results. And here we can filter on different other parameters and create actually really, really complicated compound queries, like different different cancer types and a really, really complicated query. But Samply.Beam does not really care how the query looks. It's just for transporting those messages. So this was one of our applications. And I think foreseeing that the model of task and result makes sense. The interface sends a task, give me all those patients to the local sites. They can query their databases and return the results. Okay, let's get a little bit deeper into Samply.Beam, how it works. I try to stay on the surface of the technological level, but let's get a little bit deeper. So as I said, we have some local components, mainly the Beam proxy, and we have some central components. And each of these components has a unique hierarchical ID. That means the Beam broker, the heart of the network, the component actually distributing the tasks, has the name beam.example.org. And on the left-hand side, the Beam proxy has the ID site.a.beam.example.org, and the application has the ID app1.site.a.beam.example.org. And I think you can get the gist. The ID is responsible for setting up a kind of hierarchy of responsibility. So not every system in the network needs to know how the systems in the other sites are set up. It just had its own limited view and its own limited responsibility. For example, the Beam broker doesn't need to know which applications are connected to it. The Beam broker just needs to know the Beam proxy is connected to it, and those are enrolled through a certificate authority to guarantee those cryptographical securities. And this is just the view of the broker. And the Beam proxy just needs to know which applications are enrolled to them. And just this local view is important for that Beam proxy. And we designed it that way to reduce the setup difficulties we ordinarily have when we use the commonly deployed security infrastructures like in internet scale, where we have domain name systems and public key infrastructure systems, which have quite a lot of foot guns to set up and to operate. And for most research networks, we don't need this scale. So we have like dozens or hundreds of participants. And for that, our custom and a little bit stripped down addressing scheme and certification scheme works really, really well and reduces the complexity in the operation. So what is actually a Beam task? Let's generalize it a little bit. When we think of an ordinary post envelope, we have a lot of similar information on there. We have a recipient, of course, otherwise we couldn't route the envelope at all. We have a sender as a return address. Maybe we have some metadata like a printed on company logo, or we have delivery instructions like do not forward or confidential. And then, of course, most importantly, we have the letter. And what's actually in the letter, we don't care. It can be a poem, it can be an invoice, it can be loose change. For the postal service, it doesn't make a difference. And the Beam task is quite the same way. We have an identifier, but we have recipients in the to field. We have a sender in the from field. We have some metadata for filtering or prioritizing. And then we have some delivery instructions like how to deal with the failure of delivery. In this case, retry it 5 times. Or the TTL means time to live. A lot of queries just make sense in a specific time frame. For example, this query just makes sense in the time frame after 30 seconds. It's useless, so just discard this message, discard this task. And then we have the body, which corresponds to the letter. And there everything goes. Every string, every binary sequence, everything a service might want to transport can go in there. In this case, it's inspired by this feasibility query. So we're searching for age greater than 40 and age less than 75 as an example. And only the application, only the recipient needs to interpret this body. Nothing in the Beam networks uses this body. It can't use it because it's encrypted, but the application needs to understand it somehow. And the result is a lot the same way. We have a recipient, we have a sender, we have an associated task. So the result always associates to a task that was sent. We have a status and again a body. And the status is interesting because it can give a little bit of management view of those tasks. We can get a lot different information, like if a task is claimed, that means it's received and the node is working on it, or whether the computation already succeeded with a response, or it's temporarily failed or permanently failed. And then we can give additional details to all those statuses. So I've made some claims about efficiency and security, and I want to talk about one concept we use for efficient communication, and that is the horribly named long polling mechanism. It's horribly named because oftentimes long polling is very, very quick and much quicker than ordinary polling. So let's introduce it. First, the classical polling, and this is one way to deal with those firewall restrictions. Instead of having a bidirectional communication, we have Alice just asking Bob in regular intervals whether a task is available. So Alice writes, "Is a task available for me?" and sends it to Bob. And Bob answers, looks into his table and answers, "No, I have no task for you, Alice," and sends this reply back. And 15 seconds later or so, or 10 seconds later, Alice asks again, "Is a task available?" And still no task is available. And then the third time, she asks again, "Is a task available?" And this time, a task, Bob received a task for Alice, and he can reply with the correct task. And this works. It's a quite naive way to deal with those network requirements, and it works, but it's really inefficient. For example, imagine that Bob received the task for Alice half a second after he sent his last reply, and then we have to wait 15 seconds until Alice asks again and receives the reply. And all those delays add up, and it's quite noticeable in a user interface when we click the button and only receive an answer like 15 or 20 seconds later. So we used long polling, and the model of long polling is more like in the example shown below, where Alice used the enclosed return envelope to send me one task and sends this message over. And then Bob waits until he receives this one task and immediately replies with a task. And this is quite easy to use for the applications. For example, for receiving task, we have this query. We just ask local proxy, "Give me all the tasks with a filter." The filter in this case is to do, which means they are addressed to me and I haven't sent a reply already. And then we have these long polling parameters like wait count, wait until you receive 3 tasks. We can, or the application can determine in which batch sizes the application wants to receive tasks or even results. In the feasibility query I showed, we know how many sites are available, and we can instruct just return the results after all sites have answered, for example. Or we have a second condition, a wait time. Give me all the results you have when those 10 seconds exceeded, for example. And this is really easy to use for the applications, and everything behind with timeouts and retries is used very transparently by the Beam proxy. So let's give a short summary. I think what I want to highlight the most is, for a client perspective, the usage of Samply.Beam is really, really, really easy. We talked a bit about the intricacies of the mechanisms and stuff like that, but it really doesn't matter for the applications. Depending on whether you're creating a task or a message or answering to a task or a message, it's a 3-step process. With the first, for the creation, the first step is you create a task and send it to your local Beam proxy. Then you instruct the Beam proxy to wait for the required results. And then you receive the results and use them. So it's really, really easy to use. And for the answering service, it's quite the same. You instruct the Beam proxy to wait for a task assigned to you. Then you receive them, claim them, work on them, and send back the results. And that's it. And we're quite confident that the usage of Samply.Beam has a lot of benefits. Like, as I said, we try to combine all those esoteric systems we encountered in practice in the medical research networks we worked in the last decade. And in all those strange systems, it worked quite well out of the box. And it's fully compatible with a lot of data protection concepts, and is especially designed for secure data communication in complex networks. So it's highly performant, even if those strange systems are in place, or those strict systems are in place. It requires no inbound connections, no DMZ components, which are oftentimes very difficult to get from your local IT department. It provides all the usual communication patterns we have encountered. It has a very high level of security by end-to-end signatures and encryption. It's written in the Rust programming language, which allows for a very robust and safe software component. It's very lightweight and economical, both in disk size and memory usage. And it deals with all the network plumbing that otherwise the applications has to deal with. It's the last point, 2 points I combine together. It's really easy to extend because it's fully open source. The complete code, the complete documentation, the complete specifications for the REST interfaces are open source and can easily be seen, can easily be adapted to the own use case. But to elaborate on the last thing a bit, a couple of months ago, my colleague Galina Tremper held a talk in this ToolTalk series about the MindSolist pseudonymization service we developed. And in the last years, the MindSolist really became a community-driven product with code contributions and feature contributions from a lot of different users and different using sites. And we really, really want Samply.Beam to become a product for the community, from the community as well. So please check out our GitHub repository. Please contribute your code. Please participate in the roadmap design, and feature requests are always welcome. We would really, really like to broaden our scopes and broaden our scope out of just the medical realm and hear of your pain points and work on them and see how Samply.Beam might alleviate a lot of these issues. So with that, thank you for your attention. And I think I'm open for questions. And again, please check out our repository with all the documentation and all the code. Thank you.
So thank you very much for your great presentation and the insights. Samply.Beam offers a whole repertoire of possibilities, from communication parameters, authentication, authorization, end-to-end encryption. I think it's a very exciting work, and I am looking forward to your questions and further discussions. So the live streaming will now end, and you will have the